Hello everyone, in this video we're going to be going through our 2024 predicted paper for Edexcel IGCSE Double Science, and this is Chemistry Paper 1. Now, after the question comes up on screen, I want you to pause the video. Yes, we do, pause the video. Have a go at it yourself on a bit of paper, play the video, and then watch Charlotte work through the answers. Were you picking up on all the correct mark words? Have you laid out your answer correctly to show the examiner that you can get all of the marks possible? What do you need to improve on for the real exam?
Here we are told that calcium reacts with oxygen to form calcium oxide. We're told that calcium is a metal. And we're asked in this question to describe how the position of calcium on the periodic table tells us that it is a metal. So here, this is a little bit of knowledge that you're expected to know about the periodic table. So we find metals over on the left-hand side of the periodic table, whereas the non-metals are found over on the right-hand side. So if you were to look at a periodic table, look for calcium, which is in group 2, you can see that it is indeed on the left-hand side of the periodic table. Okay, so for part B, we're told that the electronic structure of calcium is 2882. And we're asked to complete the diagram below to show the electronic structure of oxygen. So if we were to look at the periodic table of oxygen, we would see that down at the bottom we have an 8 and on the top we have 16. Now that number on the top is the mass number, or the atomic mass of the oxygen, whereas the 8 is the proton number, or the atomic number of oxygen. Now, what it's important that we know is that if we have an atom, then the number of the protons is equal to the number of the electrons. So that means that we know then that oxygen has 8 electrons in total. Now, for electronic structure in the first shell of an atom, we can have 2 electrons. Whereas in subsequent shells, we can fit as many as 8 electrons. So we have 8 electrons to play with, we put 2 in the first shell, and that leaves us with 6 electrons left to fit into oxygen's outer shell. And that in total, you can see, gives us 8 electrons. So that there is the electronic structure of oxygen in diagram form. If we were to write it in a similar way to how calcium's was, we'd write it as 2, 6. So that there shows 2 different ways in which we can write down the electronic structure of oxygen, but of course they wanted us to draw it using the shells, which is why they gave us the diagram here. So in part C here, we're given the reaction between calcium and oxygen. We're told that 2 calciums react with oxygen to make 2 CaO. And here we're told to describe in terms of electron transfer what happens when calcium reacts with oxygen. So this is a 4 marker, but actually it's not going to take much to acquire those marks. Really, we need to understand what is happening to calcium and oxygen in terms of losing and gaining electrons. So calcium, as we know that it has the electronic structure of 2882, you can see that it has 2 electrons in its outer shell. So 2 electrons in its outer shell means that to gain a full outer shell, it needs to lose 2 electrons. So for that reason, calcium loses 2 electrons. Now that there is already 2 marks, because by understanding that calcium is losing electron, we get a mark. And by understanding the number of electrons it is going to lose, we get our second mark. So now we want to do the same with oxygen. And the electronic structure of oxygen was 2, 6. So its outer shell contained 6 electrons. So to get that full outer shell, and remember that 8 electrons represents a full outer shell in all but the most innermost shell, we're going to need to gain 2 electrons, aren't we, to get it up to 8. Of course, alternatively, we could lose 6 electrons, But that's going to be much more work for this oxygen atom than simply gaining 2, which is a much smaller number. So here we can say that oxygen is going to gain 2 electrons. So here we get another mark for stating that oxygen is gaining electrons, and our final mark for saying that it is gaining 2 electrons. So there we go, that there is our 4 marks. It's actually not as bad as it seems. And I would always say that it's all about using those key words. Don't feel like you need to be writing essays. Just get those keywords into your questions. So next up, we're asked to draw a dot and cross diagram of calcium oxide and show the outer electrons only. So whenever I'm asked to draw a dot and cross diagram, there's always one thing I want to start by narrowing down. There's 2 types of dot and cross diagram, and we need to make sure we know which one is relevant to this particular question. So there is the one with the square brackets and the little charges up above, and there's also the one with the overlapping circles, okay? Now those are completely correct in the right context, but there is a right and a wrong answer, dependent on what substance we're being asked to do the dot and cross diagram of. Because this first dot and cross diagram with the square brackets and the charges is for ionic structures, whereas this second one with the overlapping circles we use for covalent structures. And to be able to identify whether what we have is an ionic or a covalent structure, you need to look at the elements that are composing it. So covalent structures are going to be made up of just nonmetals. So it could be nonmetals bonded to other nonmetals, but you'll just exclusively have nonmetals. So with ionic substances though, they are composed of a nonmetal and a metal. So if we go and look at calcium oxide, we know that the calcium is a metal, but the oxygen is a nonmetal. So you can see here that we are going to have to use the ionic dot and cross. And I think narrowing this down and not knowing that we really need to think about this is one of the number one ways in which we can make mistakes in these questions and go the wrong direction and not actually get any marks. So here, to do this dot and cross diagram, we can use our answer to part 1 of C. So for calcium, we knew that initially we had 2 electrons in the outer shell, but then we lost them, didn't we? And by losing 2 electrons, 2 negative things, we're going to form a positive ion, a 2+ ion. Don't forget that electrons are negative things. Imagine you have lots of negative thoughts and you get rid of them, you feel really positive, don't you? Just like this calcium ion will be too. And this again is another very, very common mistake that people make. The thought of losing something, you think, oh, that's negative, so it should be a negative charge. But no, you're losing negative particles, which actually makes it positively charged. So the calcium ion will just look like this. We'll just do an empty circle because we've lost those 2 electrons, and then now we have a 2+ charge. Over on the oxygen, on the other hand, we know that it did have 6 electrons in its outer shell, but then it ended up gaining 2 electrons over from the calcium. So I'm going to do 2 circles, and of course instead you could have done 6 dots and 2 crosses. It works out exactly the same, so don't worry. So we've gained 2 electrons, which means that we've gained 2 negative things, which makes us 2- charged. So that there is our dot and cross diagram of calcium oxide. Perfect. So in this question, we're told that diamond and graphite are allotropes of carbon. And what an allotrope is something which is made of the same atom, but it's just arranged in a different structure to form something slightly different. So we've got diamond and graphite, both made up exclusively of carbon. So we're given a table with their properties. We're told that diamond doesn't conduct electricity. It has a very high melting point of 4,000 degrees C, and it is very hard. Whereas graphite is a good conductor of electricity, got a lower melting point of 3,600, and it is soft. So some very different properties there. Now these 6 markers are a little bit different to a normal question. Because with a normal question you would think, oh, it's a 2 marker or a 3 marker, you need to give that many marking points. You need to say that many significant things to get those marks. And here, although this is a 6 marker, certainly giving 6 points would be good, that isn't necessarily what's going to get you the marks. Because if you gave 6 marks about diamond, you probably wouldn't actually get many marks. Because what these 6 markers are looking for is they want you to give a high level of detail and talk about all relevant points. You want to give a full answer discussing a bit of everything, nicely balanced. But you're not necessarily going to get it for just six facts that you lay out that's relevant. It has to answer the question fully to a high level of detail. So let's have a look at how I would suggest answering this question. So here I'm going to start talking about diamond, and I'm going to discuss the structure and properties diamond has that makes it distinctive and special, and then we'll link it to its properties. So in diamond, every one of its carbon atoms forms 4 strong covalent bonds to other carbon atoms. Now that is very, very distinctive of the carbon atoms in diamond. So now we've talked about the bonding, let's mention the type of structure that diamond has. So diamond has a giant covalent structure. So let's link all this now to the properties. So we've said, haven't we, that diamond has a very high melting point of 4,000 degrees C, and it is also very hard. So we need to describe why it has those properties and how it links to what we said about the bonding and structure. So the reason why it has that very high melting point and it's very hard is because of those strong covalent bonds. It is going to take a lot of energy to overcome those bonds and to break those bonds. That is going to have a direct impact on this high melting point and it being very hard. So the next thing that we want to talk about here is why is it that it doesn't conduct electricity? Well, if we look at each carbon atom would normally have 4 electrons that it could donate to form bonds, and every single one of those does form bonds because it has 4 strong covalent bonds. As a result, there's no spare electrons, there's no delocalized electrons that would be what's needed to conduct electricity. So that's why diamond doesn't conduct. Let's get on to graphite. So in graphite, each carbon atom only forms 3 of these strong covalent bonds. So it doesn't form the 4 that diamond did. And that's one of the main differences between diamond and graphite. So if you're not 100% familiar with those differences, then I would definitely recommend that you make yourself a little flashcard with a nice table comparing the two. So graphite, we've mentioned that each carbon forms only 3 strong covalent bonds. Now we can link it to the properties of graphite. So we can see in the table that there's a lower melting point for graphite and it's also soft. And the reason for that is that graphite forms layers. And those layers, they don't have these strong covalent bonds between them. They've only got weak intermolecular forces. And as a result of these weak intermolecular forces, it's going to be really quite easy to overcome these forces. And so for that reason, we don't have as many strong bonds to break. We've got some that are actually quite weak. And then we have that knock-on effect there of that lowering the melting point and making it softer. So then the final thing really to mention about the properties of graphite is going to be about the fact that it is a good conductor of electricity. So if we think back to the fact it only forms 3 strong covalent bonds, and carbon, of course, it has 4 electrons in its outer shell. So if only 3 of those has gone to form covalent bonds, then we're going to have 1 left. And that one that's left is delocalized, which means that it is going to be free to move through the layers that are formed in graphite, and it can carry that charge. And that there is what's required for something to conduct electricity. So that is why graphite is a conductor of electricity, because it has a delocalized electron which is free to move through the layers. So let's just look at some of the key facts that's important to know about diamond and graphite, the key words that are going to bring you in the marks in an exam. So for diamond, knowing that you have 4 strong covalent bonds, that you have a giant structure, and then for graphite, that we only have 3 strong covalent bonds, and that we have layers formed. Also, the fact that graphite has 1 delocalized electron for every carbon, and in diamond you actually have no delocalized electrons. If we were to strip back everything here that we have said, those are the key facts that you can link to anything if you learn those. So I'd really recommend that you learn those key facts, draw up a nice little table in your notes to compare diamond and graphite and get learning it. And it will really impact you because these questions always come up in the exam. So here we're given a picture of another allotrope of carbon called Buckminster fullerene. Here we're asked to identify the formula of Buckminster fullerene. Now here you see it's just an identify question. This is really just testing your recall. This is just a fact that they have expected you to memorise. So the answer to this is C60. So if you don't know that already, add it to a flashcard and get memorising it. Here we're told that Buckminster fullerene has a low melting point and is slippery. And we're asked here to explain why. So in this question, the reason for this is all about its intermolecular forces. And between Buckminster fullerene molecules, there are very weak intermolecular forces. Now what this means is when we want to separate these molecules, we only need to have a very little amount of energy to overcome these forces of attraction. So that's going to directly contribute to the low melting point and the fact it's slippery. So the 2 points that we need to make to get our 2 marks in this question is that there are weak intermolecular forces between the molecules and that only a little bit of energy is needed to overcome them. The air in the atmosphere is an example of a mixture of substances, including oxygen, nitrogen, carbon dioxide, and a trace amount of argon. Here we're asked to describe the difference between a mixture and a compound. So this will really test our knowledge on what these 2 things actually are. So a mixture is a substance made up of 2 or more elements or compounds that are not actually chemically combined. So they're very easily separated. Whereas a compound is different from this, okay? So when we have a compound, we find that the elements are actually chemically combined, which means that they cannot simply be separated really easily, okay? So this here is the main difference between what a mixture and a compound actually is. So a mixture has some different substances that are not chemically combined, whereas in a compound our elements are chemically combined. And that there will be our answer. So for B, the different substances in the air can be separated. Here we're asked to identify the process that can be used to separate the substances in the air from each other. So because in the air, all of these different substances have different boiling points. Now for that reason, if we were to boil them all off at different temperatures, then we could separate them. Now we've got several substances here, haven't we? We've got oxygen, nitrogen, carbon dioxide, and other substances too. So we've got to do it lots of different times, in lots of different fractions. So our answer here is fractional distillation, whereby we're going to separate all these different substances from each other by using their boiling point. So that leads us straight on to our next question, and I feel like I've kind of given the game away here. So here we're asked to state the property of the substances in air which enables them to be separated using this method. So it is the fact that those different substances all have a different boiling point. That is the property that we're going to use to separate them all using fractional distillation. So here we're given the mass spectrum of a sample of argon as shown below. The mass spectrum shows the percentage abundance of the isotopes of the element argon, Ar. So here we're asked to state the definition of the term isotope in terms of particles. Now this is actually such an important definition for GCSE chemistry and also moving on to A-level chemistry in the future. They love this definition. So an isotope is an atom of the same element which has the same number of protons but a different number of neutrons. Okay, so it's those two facts that they really care about here. So the fact that we have the same number of protons, but we have a different number of neutrons. That there is exactly what we want to say to get our 2 marks. So if you don't already know that definition, stick it on a flashcard now. So here we're asked to use the mass spectrum provided to calculate the relative atomic mass of argon. So to do this, we need to use the little graph that they gave us. And we need to use the percentage abundances and the masses of each of those different isotopes. And what you're going to do is work out the sum of all of the percentage abundances times by the mass and then divide by 100, okay? So what that's going to look like here is we're going to do the 2 times by the 36, and then we're going to add the 3 times the 38, and then we are going to add the 95 times by the 40. And then we're going to put all those in a calculator and then finally just divide through by 100. And putting that into the calculator there, I end up getting an answer of 39.86. So that there will be our answer to this question. That is the relative atomic mass of argon from this sample. So for part D now, we're told that in the periodic table, argon is represented in this way. So we've got 40 on the top and an 18 on the bottom. We're asked to write down the number of protons, neutrons and electrons in an atom of argon-40. So it's important we remind ourselves what that top number and that bottom number mean. And it is given in the key as well of the periodic table that you will be given in your exam. So we've got an 18 at the bottom here. That bottom number is the proton or atomic number. And what that directly relates to is the number of protons within this substance. The top number is also known as the mass number or atomic mass. And in terms of particles, what that means is that is equal to the number of the protons plus the number of the neutrons. So it's the sum of protons and neutrons. So if we have a look at what we need to fill in here, we need to fill in the number of protons first. Well, we know that's 18 because we know that 18 is the proton number. So we can fill that in first. The next thing we need to fill in is the number of neutrons. And if we know that 40 is equal to the number of protons, which we've already said is 18, plus the number of neutrons, then to work out the number of neutrons, we simply need to do 40 minus 18. And so that gives us 22. So here we know that we have 22 neutrons. And then finally, we need to work out the number of electrons. Now, the number of electrons is going to be worked out slightly differently. We need to use a fact about an atom. Okay, so we need to know that whenever we have an atom, we have the same number of protons and electrons. And think about it, atoms don't have an overall charge, do they? So that means that the positive protons and the negative electrons are balanced. We have the same amount of each of them. So as we've already said that we have 18 protons here, we can confidently say that in this atom of argon, we also have 18 electrons. So that there is our completed question D. Well done.
Sulfuric acid, H2SO4, is an example of a strong acid. Here we're asked to name the ion present in sulfuric acid that makes it an acid. And the thing about acids is that this isn't specific to sulfuric acid. Any acid relies on this ion for it to be an acid. And the answer to this is the H+ ion. So whether we're dealing with sulfuric acid, ethanoic acid, nitric acid, hydrochloric acid, all of these will release H+ ions when in water. And so that is the ion that makes them acids. Now we're told when an alkali is added to the acid, a neutralization reaction takes place. Here we're asked to write down the ionic equation that represents a neutralization reaction. And we're asked here to include state symbols. This is a reaction that really we need to go away and learn, but there's certainly some understanding behind it too. So we've just said that the H+ ion is what every acid has. So when we have a neutralization reaction between an acid and an alkali, that's going to be an H+ ion plus the ion responsible for alkalis. And that ion is the OH- ion. So here essentially we have an acid plus an alkali, and they generally make a salt plus water. Now the salt doesn't have a place in this ionic equation, so we just need to do an arrow and then make water, which if we look at what we have in the reactants there, we have an H and an OH. It makes H2O, doesn't it? So it makes sense. So now that we've got H+ plus OH- makes H2O, we can have a look at the state symbols. So both H+ and OH- are found in solution, which means that they are aqueous. Water, on the other hand, is a liquid, so we're going to write a little L in brackets next to the water. And there we have the ionic equation that represents a neutralization reaction. And we can just go away and learn this because it's going to come up time and time again. Now we're asked to identify the pH of the solution formed in a neutralization reaction. Well, it's very important that we know that the neutral pH is 7. Any pHs lower than 7 are acidic, and any pHs higher than 7 are alkali. So we need to know that scale of pHs, knowing that 7 sits right in the middle, making a neutral solution. 4 test tubes, each with a different metal, had 20 centimetre cubed of dilute sulfuric acid added to them. Their observations were recorded below. So here we can see that when we added sodium, there was a violent reaction. When we added gold, there was no reaction. When we added zinc, bubbles of gas formed and the metal dissolved. And with calcium, the bubbles of gas rapidly released and heat was given off. Here we're asked to write the names of the 4 metals in order of reactivity using the information provided in the table. So what I would start off doing here is by going for the 2 extremes, the most reactive and the least reactive. So out of these, the most reactive is clearly going to be the sodium, which had a violent reaction, which is much more vigorous than any of the other reactions that they've observed here. So for most reactive, I'm going to put sodium. Next up, I'm going to find the least reactive. And looking at these observations, the one which is the least reactive is surely the gold, which has no reaction. So gold, no reaction, is going to be the least reactive. Now we've got the middle 2 positions, which we need to put a little bit more thought into. So both zinc and calcium have quite similar observations here. For zinc, bubbles of gas formed and the metal dissolved. Whereas with calcium, bubbles of gas were rapidly released and heat given off. So here, for me, it's that rapid release of gas that makes the difference here. here I can see that the calcium must be more reactive than zinc, because both of them gave off bubbles, calcium gave them off more rapidly. So underneath sodium here, I'm going to put calcium. And underneath calcium will go zinc. So the order of reactivity of these four metals is going to be sodium, calcium, zinc, and then gold. So now we're asked to give the word equation for the reaction between zinc and sulfuric acid. So to answer this, let's first recap with what that general reaction is between a metal and an acid, because this is the fact that we're going to use here. So a metal and an acid will make a salt plus hydrogen. And it's really important that we have that memorized. You can use the acronym MASH to help you. So now the last little thing I'm going to remind you of before we actually answer the question is that whenever we have sulfuric acid and it forms a salt, it will form a sulfate salt. And that's really going to help us here. So let's use our metal plus acid, make salt and hydrogen to write this answer. So here we've got zinc plus sulfuric acid is going to make a salt plus hydrogen. To work out which salt, it's going to be the zinc and the sulfate. So it's going to be zinc sulfate plus hydrogen. And that there is the word equation for the reaction between zinc and sulfuric acid. Acids can react with different substances to form salts. The salts formed are sometimes soluble and sometimes insoluble, forming a precipitate. You were asked to complete the table below to show the salt produced in the reaction and whether the salt is soluble or insoluble. So the first thing we need to do is work out what is made when we react these things together. Let's remind ourselves what kind of salt is formed when we use nitric acid in a reaction. So nitric acid will always make a nitrate salt, and sulfuric acid will always make a sulfate salt. Now that we know this, it's quite easy piecing together which salt is made. We look at the metal of substance X and that part of the acid name. So this is going to be sodium nitrate that is formed. And that will be the salt produced when sodium carbonate and nitric acid react. Next up, if we look at the calcium and the sulfuric acid, so the sulfate, we're going to get calcium sulfate as our salt formed. And already we've got 2 out of the 4 marks, so we're doing brilliantly. Now we need to determine if they're soluble or insoluble though. This is the tricky bit. We have to have memorized this or we just can't do it. So we need to remember that nitrates are always soluble. That's quite an easy one. There's no exceptions to the rule with nitrates. We just need to know that all nitrates are soluble. So therefore, sodium nitrate is soluble. Now for the sulfates, it's a little bit trickier. So for sulfates, we need to know that most of them are soluble, except 3 particular ones. Okay, so I'm going to tell you the exceptions here. So all sulfates are soluble except barium, lead, and calcium. And of course, it's the fact that it's calcium that is not soluble, which is going to determine our final answer here. So for calcium sulfate, we're going to say that that salt is insoluble. Iron is a transition metal and it has many uses, ranging from the construction of bridges to saucepans used in the home. One problem with the use of iron is that it can rust, and when iron rusts, it becomes weaker. Here we're asked to write down the word equation for the rusting of iron. This equation is one that we need to learn. So we need to know that iron plus water plus oxygen, the 2 things needed to be added to iron for rust to happen, makes hydrated iron 3 oxide. And notice we don't just say makes rust.
I think the trickiest bit of this equation is that product, hydrated iron 3 oxide with Roman numerals for the 3. So if you don't know that already, get learning it. So now one method of preventing an object made of iron from rusting is oiling it. Here we're asked to explain how oiling an iron object will prevent it from rusting. And there's 3 key points here. One is just understanding that it acts as a barrier, and that applies to other substances too. That oil acts as a barrier in this case. And then we need to express what it's acting as a barrier to. So it acts as a barrier to oxygen and water, and that is where our 3 marks are coming from here. One of the methods used by shipbuilders to prevent rust is sacrificial protection. Here we're asked to explain how sacrificial protection prevents the rusting of the ship's steel. So we need to have 3 points here for this 3-mark question. So the first thing we want to state is the fact that a block of zinc is added to the steel of the ship. So it might seem odd, but literally you get a big block of zinc and you attach it to the steel of that ship. The reason why we do this is because zinc is more reactive than the steel. Well, you could say iron here because, of course, steel is an alloy of iron. So, because it's more reactive than that steel, that means that rather than the steel reacting with the oxygen and the water, the zinc will actually react with it instead, meaning that any corrosion is going to happen to the zinc rather than the steel. So those are our 3 key points that we want to make in this question. First off, we just want to state what we do with the zinc. So we add a block of zinc to the steel of the ship. Then we state the really important fact that zinc is more reactive than the iron or the steel of the ship. And as a result of that, the zinc will react with the air and the water more easily than the iron or the steel. Notice here I've been comparative throughout. I've said zinc is more reactive and zinc reacts more easily with the air and the water. All of those comparative statements are really critical to getting your marks in this question. Here we're told that group 0 molecules are known as the noble gases. Noble gases such as helium are monatomic and unreactive. Here we're asked to explain why noble gases are unreactive. So the reason why noble gases are unreactive is, of course, they're in group 0, which is sometimes otherwise known as group 8, which means that they all have 8 electrons in their outer shell. Now, when things react, they're generally trying to acquire this full outer shell of electrons. So noble gases are unreactive because they actually already have this full outer shell of electrons. In part B, we're given a graph which shows the trend of boiling points for the different noble gases. We're asked here to describe the relationship between the boiling point of the noble gases and the number of shells. So let's start here by having a look at the group 0, and I'm just writing down those elements as you go down the group. And let's remember how many shells each of these has. Helium just has 1, neon has 2, argon has 3, krypton has 4, etc, etc, etc. So as we go down the group, we have an increasing number of shells. So if we go back to our little graph here, we can remember that as we go along here, we have an increasing number of shells. So now that we know that and we know the link between these different group 0 elements, we can relate it to this question. So now when we look at this graph, we can say that as there are more shells in the group 0 element, the boiling point increases. And you can see that because each of these bars, as the number of shells increases, the boiling point does indeed get bigger. So that would be our description of the relationship between the boiling point and the number of shells. So now we're asked to use our knowledge of intermolecular forces to explain this relationship that we just described, that as the number of shells increases, the boiling point increases too. So you can see here this question is a 3-mark question. Now that means we need 3 valuable points as to why this relationship occurs. So the first thing to say is that as we have a greater number of shells, the particles get greater in size as well. Now this is going to have a knock-on effect on the intermolecular forces between the particles. So that is because as the particles get bigger and have a greater size, there are going to be stronger intermolecular forces between those particles, which means that there's a greater pull between those different molecules, a greater attraction. So when we have greater or stronger intermolecular forces, that means that if we want to boil or change the state of this substance from a liquid to a gas, we're going to need to put in more heat energy to do this. So this is going to be why, as the number of shells increases, the boiling point also increases. So let's just quickly recap that, okay? So as the number of shells increases, the particles get bigger in size as well. Now, when we have bigger particles, we have stronger intermolecular forces. And as a result, we're going to need more heat energy to overcome those forces and boil the substance. So in part C, we're told that group 7 elements such as fluorine, chlorine and bromine are diatomic molecules. Here we're asked to state what the group 7 elements are also known as. So because this says state, this is really just a fact that we're expected to just know, okay? So the group 7 elements are otherwise known as the halogens. So that's a nice speedy mark there, and it is just a pure recall fact. There's no understanding to it at all. So if you didn't already know this, stick it on a flashcard because it's likely to come up at some point. So now we're asked to complete the dot and cross diagram for chlorine. So here this question helps us out a little because they've drawn the overlapping circles. So straight away we know that this is the type of dot and cross diagram we need to draw, the one with the overlapping circles. Now, as we're told earlier, chlorine is in group 7, and group 7 elements all have 7 electrons in their outer shell. That's one of their distinctive features. So each of them have 7 electrons in their outer shell. They need to gain 1 electron to get that full outer shell. And of course, we need this full outer shell to be nice and happy and content as a chlorine molecule. So when we need to do these dot and cross diagrams that have overlapping circles, there's a little rule that we need to remember. And so for every 1 electron we put into the overlapping shell, the other atom has to put 1 in as well. And that there forms the covalent bond, which is the shared pair of electrons. So we're not going to see just 1 in on its own. We're always going to see them in multiples of 2. So there's going to be 2, or there's going to be 4, or there's going to be 6, or so on. So here we know that each chlorine needs to gain 1 electron. So if it needs to gain 1 electron, then it's going to have to put 1 in itself. So it's going to put in 1 electron, and in total it has 7 of its own electrons, but it puts 1 into the sharing region, and then the other chlorine is going to do exactly the same. It's going to return the favour by sharing 1 of its own in that region as well. So again, this other chlorine atom will also have 7 electrons in its outer shell of its own. So here we can go 1, 2, 3, 4, 5, 6, and 7, because that final one has to be in the shared region. Both of them want to gain 1 electron, so both of them have to put 1 of their own forward first to get 1 in return. And then now you'll see that each of these chlorine atoms has 8 electrons. So you've got the 1, 2, 3, 4, 5, 6, 7, 8 there. And so will the other chlorine atom as well. So you've got 1, 2, 3, 4, 5, 6, 7, 8. So there, what we have here is our dot and cross diagram for Cl2. So Cl2 reacts with potassium iodide, Ki. A reaction takes place where the chlorine displaces the iodine. So explain why the chlorine displaces the iodine from the potassium iodide. So if we remember our elements within the periodic table in group 7, so right at the top there we have our fluorine, we have chlorine, then we have bromine, and then we have iodine and astatine at the bottom. So if we compare the chlorine and the iodine, we can clearly see there that chlorine is going to have fewer shells than iodine. And therefore it's going to have a much smaller radius than the iodine well. Now, the knock-on effect of this is that there's going to be a greater attraction between the outer shell electrons in the chlorine and the nucleus. Now, that greater attraction means that if another electron was to come along here, then that chlorine is going to find it easier to gain an electron than the iodine because of that greater attraction between the nucleus and those outer shell electrons. So that is going to be why chlorine is able to displace iodine from the potassium iodide. So if we sort of think back here and just recap what I've said to get our 3 marks for our explanation as to why chlorine will displace iodine, we can see that chlorine has fewer shells than the iodine, which means that the chlorine has a greater attraction between the outer shell electrons and the nucleus. And then finally, the fact that chlorine is going to be able to gain an electron more easily than iodine. So make sure in your answers, and we've done that the whole way through here, we are comparative. See how we say fewer shells than the iodine, greater attraction, more easily. We can't just state facts, we have to be comparative in a question like this where we're comparing 2 substances.
The following apparatus were set up to investigate the energy released by the combustion of an alcohol, ethanol. We're told that the mass of ethanol was measured using a digital balance, and that 100 centimetre cubed of water was added to the flask. The temperature of the water was measured using a thermometer. The ethanol was combusted under the flask of the 100 centimetre cubed of water, and the temperature was monitored until the temperature was observed to increase by 30 degrees C. The mass of the ethanol was then recorded, and this was then repeated using propanol as the fuel instead. The results were recorded below. So here you can see this table shows 2 different alcohols, ethanol and propanol, and it shows their initial and their final masses before and after the combustion. Here we're asked to complete the table by calculating the change in mass. So if we start with ethanol, we can see the change in mass will be 83.05 minus 85.34, and that ends up giving us a change of mass equal to minus 2.29 grams. So that's the change in mass for ethanol. For propanol, we have 79.98 minus 80.58. And subtracting those, we end up getting minus 0.60 grams. Try and keep 2 decimal places there, just like all of the other answers have 2 decimal places. So now we're told that 0.05 moles of ethanol were combusted. We're asked to calculate the number of moles of propanol combusted, and we're helpfully told here that the MR of propanol is 60 grams per mole. Now to work out the moles, that's mass over the MR. And in this case, we know what the mass of propanol combusted is, because that's equal to the change in mass, and we calculated that to be 0.6 grams. So the moles of propanol will be 0.6 divided by 60, which equals 0.01. So that there is the answer for the number of moles of propanol combusted. Now we need to calculate the heat energy change during the combustion of propanol, giving our answer in joules. So for this, we need to know the equation that Q, or the energy change, is equal to mc delta T, where Q is the heat energy change. So mass refers to the mass of the thing getting heated up, and that is the 100 grams of water. C, we're told, is 4.2, and the change in temperature is 30 degrees, because remember, we looked at increasing the temperature in this experiment by 30 degrees. So Q will equal 100 times by 4.2 times by 30. And if we put that into our calculator, we find that the heat energy change is equal to 12,600 joules. And that there's the answer. Now we're asked to calculate the molar enthalpy change, delta H, when propanol is combusted, and we're asked to give our answer in kilojoules per mole and include a sign in our answer. So it's important that we know that molar enthalpy change is calculated by taking our Q and dividing it by the number of moles. So, of course, here they've said we need the answer in kilojoules per mole. Well, at the moment we know that Q is equal to 12,600 joules. To be able to work out this molar enthalpy change, we need to work out what Q is in kilojoules. And we do that simply by dividing through by 1,000. So Q will be equal to 12.6 kilojoules. So now we know Q in kilojoules, and we worked out the moles earlier as well. We can put these numbers into our formula for delta H, and we will have our answer. So that molar enthalpy change, delta H, will be equal to 12.6 divided by 0.01. And that gives us 1,260 kilojoules per mole. The final thing to keep an eye out for is notice it says include a sign in your answer. Now what this refers to is this delta H, is it exothermic or is it endothermic? Does heat energy get taken in or given out? And in this case, we know that on burning this fuel, we gave out heat energy because it caused the water to increase in temperature by those 30 degrees. And whenever we have an increase in temperature, we have a negative molar enthalpy change. And that tells us that we had something that's exothermic happening. If it was an endothermic reaction and the temperature was actually decreasing, then that means that we would have a positive molar enthalpy change. Our answer here will be minus 1,260 kilojoules per mole. Now we're told that the actual energy released by the combustion of ethanol and propanol was found to differ from the experimental results by 25% and 29% respectively. Here we're asked to name two sources of error in this experiment and to suggest how to reduce them. So notice there's two parts of that question. Firstly, we need to name two sources of error, and for each of those sources of error, we need to suggest how we can reduce them. And that's how we're going to get the 4 marks here. So the first potential source of error that I would talk about is the potential heat loss to the surrounding. Of course, when we're burning this fuel and it's heating up this water, not all of that heat energy will heat the water. Some of it will heat up the air around the water as well. So the best way to fix this is to insulate the water container, and that will minimise the heat loss to the surrounding. The second source of error is incomplete combustion taking place. So when we're burning this fuel, there's a chance that we don't simply have complete combustion, and we're getting less energy out of this combustion than we potentially could because we have incomplete combustion. Now, the only way to ensure that we don't have incomplete combustion happening is to ensure lots and lots of ventilation, to ensure that enough oxygen is able to get to this combustion. So those are my 2 points, my 2 sources of error in the experiment, and my suggestions as to how I can reduce them. Hydrogen peroxide solution, H2O2, decomposes on addition of a catalyst. The equation for the decomposition of hydrogen peroxide solution is shown below. Here we're asked to complete the equation by adding the state symbols in the spaces provided. So here we need to know what each of these things are. Hydrogen peroxide could be a tricky one, but if you notice earlier in the question, they've told us that it's hydrogen peroxide solution. So for that reason, we're going to write H2O2 AQ, because any solution is aqueous. Then that decomposes to 2H2O. H2O is a liquid, unless it is stated otherwise, like they say that we have steam or something, and oxygen. Now, oxygen is a gas. So that would be our answer. We're going to write aqueous for hydrogen peroxide solution, liquid for water, and gas for oxygen. Next up, we're asked to describe what's meant by the term catalyst. And this is a definition that we need to know and have memorised. So we need to know that a catalyst is a substance that is going to speed up the rate of reaction. And it is going to do this by providing an alternative pathway with a lower activation energy. And those are our two key points we want to say when we're describing the term catalyst. So to recap, a catalyst is a substance which increases the rate of reaction without being used up. And they do this by providing a different pathway or an alternative pathway with a lower activation energy. And if you don't have this definition already in your memory or in your notes, then now is the time to pause the video and to make a note of that. So now we have an experiment, okay? The apparatus shown in the diagram below was set up at 25 degrees C to measure the rate of decomposition of hydrogen peroxide. The following procedure was followed. 50 centimetre cubed of hydrogen peroxide solution was added to a conical flask. A measuring cylinder was filled with water and then inverted in the water trough. A rubber bung was connected to the conical flask, and the delivery tube was placed in the inverted measuring cylinder. The volume of gas displacing the water in the measuring cylinder was measured and recorded every 10 seconds. And here in this table, we can see our results. Now we're asked to plot the results on the graph below. So if we go through that point by point, firstly we need to remember that the time is on the x-axis and the volume is on the y-axis. So our very first point here is 0, 0. It's going to be 0 in the x and 0 up. So we just have 0, 0. Then we are told that we need to have 10 on the x-axis and 27 on the y-axis. Now, do be careful with what each little increment counts for on the y-axis and the x-axis as well. So here we can see that there's 5 tiny little squares between 20 and 30. That means that each of those little squares represents 2. So if we need to make a marking for 27 here, we need it to be halfway between 26 and 28. So we've got 10, and then we're going to do a point just here. So next up we have got 20. 20 and 45. 20, 45 is going to be halfway between 40 and 50. Then for the next one, we have 30 and 60. That should be quite an easy one to plot. 30, 60, because it's on the exact lines there. Same goes for this next one, 40 and 70. 40 and then up to 70. The next one is 50, 50. So put 50 along and 50 up. Then our next one is 60, 87. And so we'll go along the x-axis to 60. Then to get to 87, we need to go up halfway between 86 and 88. It's going to be just here. And then the next one is going to be 70, 90. 70, 90. And then the last one is 80, 90. So those two are quite easy to plot. So we have done that. For 1 mark, we need to get all those points correct. Now we need to circle the anomalous point. And what an anomalous point is one that doesn't follow a pattern. And here, if we see all of these points, they all seem to follow a line, except one, except this one here, which is my anomalous point. And in part 3, we're asked to draw the line of best fit. Now at GCSE, we're expected to know if that's going to be a straight line or a curve by looking at the trend and seeing what would fit best. Now this to me looks like a nice smooth curve that's going to flatten off at the end. It's important we know that we ignore the anomalous points when drawing lines of best fit. So let me have a go at doing this line of best fit, which is actually a curve. So I'm going through, going through, going through. I ignore that anomalous point. And this here is my line of best fit. Now we're told that the procedure was repeated, but this time a catalyst of 1 gram was added to the hydrogen peroxide solution. The volume of gas evolved every 10 seconds was measured and recorded. And you can see here, the results are plotted on graph number 2 here. Now we're told that the temperature was increased from 25 to 50 degrees C. We're asked to draw a curve on graph 2 to show the volume of gas formed with time at a higher temperature. And we need to label it X. Well, the thing to notice here is when we have a higher temperature, we know that the rate of reaction increases. And if the rate of reaction increases, that means that we're going to reach that endpoint faster. However, just increasing the temperature doesn't change the amount of reactants that we have. And as a result, we're still going to make the same amount of product, we're just going to make it faster. So the 2 things we need to look out for when drawing this curve is 1, we want it to be steeper than the original curve, and second, we want it to plateau at the same point. We want it to plateau at about 90 centimetres cubed. So the 2 things that we need to show in our curve is 1, that it is a steeper gradient, and 2, that the plateau is at that same volume of 90 centimetres cubed. And of course, don't forget to finally label it with an X. Finally here, we're asked to explain the effect that an increase of temperature has on the rate of reaction. So they're not asking us, what is the effect? They want us to explain the effect. So we need to say why it is that an increase in temperature increases the rate of reaction. As you can see, this is a 3-mark question, so we need 3 good points. Now, the first thing to state is that at higher temperatures, particles have more kinetic energy, which of course means those particles are moving with a greater velocity as well. Now, because they're moving more quickly, that means that there will be a greater frequency of collisions. So there's more collisions happening per unit time. And that is a really critical statement. Now, due to this greater frequency of collisions, more of these collisions will exceed the activation energy, thereby increasing the rate of reaction. And those are the 3 key points that we want to get across in our answer here. So if we summarise quickly, there is more kinetic energy, therefore there's a greater frequency of collisions, with frequency really being the key word there, and therefore more collisions will exceed the activation energy, and that's what increases the rate. Crude oil is a mixture of different alkanes. In its original state, it's not very useful, as different alkanes can have very different properties. The graph below shows how boiling points change dependent on the relative length of the hydrocarbon chain, measured in terms of the number of carbon atoms. So here you can see you've got a graph, carbon atoms, and boiling point. Here we're asked to describe the trend shown by the graph. So here you can see this is a 2-mark question. So in this describe, we need 2 good points. The first point is always the most obvious one. Okay, so if we look at this, we can clearly see a trend. We can see that as the number of carbon atoms increase, the boiling point also increases. You can see that due to the positive correlation on the graph. So I would always start these describe questions with the most obvious statement. After that most obvious statement, though, I'd look at it in a bit more detail. And here I can see that at the lower number of carbon atoms, so this region, I can see that the boiling point is going to increase more rapidly compared to when there are more carbon atoms. So the second point we can make is that the boiling point increases more rapidly with fewer carbon atoms compared to more. 2 key points: the number of carbon atoms increases and the boiling point increases. And secondly, that the boiling point increases more rapidly with fewer carbon atoms. So now we need to explain this trend and use our chemistry knowledge to explain why this is happening. It's another 2 marker. So the first statement we want to make is that as the number of carbon atoms increase, we're going to have more intermolecular forces. So we can start by stating something along the lines of hydrocarbons with more carbon atoms are longer and therefore have stronger intermolecular forces. Now, the second point we want to make links these stronger intermolecular forces to the boiling point. So as we have stronger intermolecular forces, more energy is going to be needed to break these bonds or to overcome these forces. And so as a result, we have a higher boiling point. The crude oil can be separated into different fractions, small groups of alkanes with similar lengths using a process called fractional distillation. These different fractions have similar enough properties for them to be useful. The table below shows some of the different fractions obtained using fractional distillation and the corresponding carbon lengths. Here we're asked to explain how the different fractions in crude oil are separated. So we need to explain how it is that this happens using our chemistry knowledge. Now there's actually quite a lot of things you could say here to get those 3 marks. So I'm going to run you through the full story, and then you can write down whichever points you're most comfortable with, though I would recommend learning it all. Okay, so the first thing we want to state is that the fractionating column has a temperature gradient. It is actually hotter at the bottom and cooler at the top. So the next thing that we can state is that the crude oil gets heated in the furnace, and because it's heated, it turns to a vapour. So it becomes a gas. So once it becomes a gas, it is going to rise up through the fractionating column. And as it rises through it, it experiences that temperature gradient. So as it rises, the vapours will condense when they cool enough. Remember that vapour is made up of lots of different components of different carbon chain lengths. So as these vapours rise up, they're going to condense at different points, dependent on when they become cool enough. Now, finally, we will conclude with the fact that the different fractions will leave the column at different points. And that is when we can collect our different fractions. And those are our key points, our little story about fractional distillation. And the key things we want to state here in this question starts off with first us having a temperature gradient in this fractionating column. It's a really important point that. Then the fact that the crude oil turns to vapour and rises through the column, and then it condenses when it becomes cool enough, leaving the column at different points. Those will be the main points we want. We only need to write down 3 of those to get our 3 marks. Here we're told that some alkanes are combusted to release energy. Here we're asked to complete the dot and cross diagram for ethane, C2H6. Okay, so I'm going to draw this here myself, nice and big, then we can add to it. So every point where these circles overlap, we need a pair of electrons. And at this level, we learn that 1 electron is going to come from each of the 2 circles. So here you can see we have carbon. We have 2 carbons. Let's zoom in on this circle here to begin with. We should remember, and if we don't, we can have a look, that in the periodic table, we know that carbon has 4 electrons in its outer shell. Due to the fact it's in group 4, that's how the periodic table can help us. So if it has 4 electrons in its outer shell, let's put 1 in each of these overlapping circles. Okay, looking good. So now if we do exactly the same thing for the other carbon, we use the fact that each carbon has 4 pairs of electrons in its outer shell, and we put them into each of these overlapping regions. You'll notice that we have here 2 electrons. Now, a shared pair of electrons makes a covalent bond. So what we've just shown here is that there is a covalent bond between the 2 carbons. Next up, let's have a look at the hydrogens. So we should be familiar with the fact that hydrogen has 1 electron in its outer shell. And to gain a full outer shell, hydrogen, because it's just in the first shell, just needs to gain 1 more. It needs to gain 1 more electron to get its full outer shell. Well, notice that if the hydrogen takes its 1 electron and puts it in the shared region, where carbon is already donating 1 of its own electrons, it now has 2 electrons in its outer shell. So we have a full outer shell for hydrogen. We can do that for all of the other hydrogens here as well. Each of them, if they take their 1 electron and put it into this shared overlapping region, then they now all end up with 2 electrons of their own. And if we take a moment here and look at each of the carbons, if we go back to our carbons here, this region, if you count up how many electrons that now has, it has 8. And so again, that also has a full outer shell. If we do the same for this other carbon, it also has 8 electrons now, which means that also has a full outer shell. So this here is our completed dot and cross diagram for ethane. Now we're asked to write down the balanced equation for the complete combustion of ethane. Well, they've given us the formula for ethane up above. We know it's C2H6. And we're expected to know that when we have complete combustion, the fuel will react with oxygen, it will burn with oxygen, and it will make 2 products only. It makes carbon dioxide and water. So looking at this, we need to balance it now. I can see that I have 2 carbons over on the reactant side. And that means we need 2 CO2s to give us those 2 carbons. Then we also have 6 hydrogens. And that means that we need to make 6 hydrogens over on the product side as well. At the moment we have H2O, each of which of those has 2 hydrogens within it. So to get 6 hydrogens, we need 3 of those. So now we're looking good. We have balanced the carbons and we have balanced the hydrogens. However, we now need to balance the oxygens. So as essentially the product side is all tied up now, I would just look at how many oxygens I have there. I can see that I have 4 oxygens within the 2 CO2s. And then I can see that I have 3 oxygens within the 3 waters. So that gives us 7 oxygens in total. And we have an O2 over here. So to get 7 oxygens, we're going to need 3.5 or 3.5 oxygens to get that. So our balanced equation is C2H6 plus 3.5 O2 makes 2 CO2 and 3 H2O. And that is our answer. Here we're told that complete combustion is preferred in industry to incomplete combustion as a method of releasing energy from fuels. By comparing complete and incomplete combustion, explain why complete combustion is preferred in industry. So there's 2 key points to make here, and of course this is a 2-mark question. So the first thing that we need to know is that complete combustion releases a lot more energy than incomplete combustion, which as a result in industry means we're going to need a lot less fuel to make the same amount of energy. So that's our first point. The second point is that incomplete combustion produces a toxic gas known as carbon monoxide. This is very dangerous to release, so we do not want to be doing this because it can kill people. So if we look back at what we've said here, the 2 key points we want to make as to why industry prefers complete combustion Firstly, more energy is released in complete combustion than incomplete. And incomplete combustion makes carbon monoxide, which is toxic, so we do not want to be making that. 3 solutions X, Y, and Z needed to be identified. The student first tested for the presence of sulfate ions. Here we're asked to describe the test for sulfate ions and include an ionic equation in your answer. So, to test for sulfate ions, we need to add dilute hydrochloric acid and barium chloride. These are the 2 things we need to add. Now, if sulfate ions are present, then we will form a white precipitate. And so that is what we're looking out for when we're testing for sulfate ions, the presence of that white precipitate. So the ionic equation for this is Ba2 plus barium ions, which are aqueous, plus those sulfate ions we're testing for, which are also aqueous, form this white precipitate of barium sulfate, which is a solid, because all precipitates are solid. And that there will get us our 3 marks. You'll get 1 mark for stating the test, so adding dilute HCl and barium chloride. The 2nd mark for the positive test of a white precipitate. And our 3rd mark for our ionic equation. The student found that X, Y, and Z do not contain sulfate ions. The student carried out further tests to determine the identity of anions in the solutions. Test 2 was carried out after test 1. The results are shown below. So, test 1 was adding dilute nitric acid, and test 2 was adding silver nitrate. We can see that in solution X, we had no change, and then we had a white precipitate after we carried out test 2. So we need to know that this is the positive test for the presence of chloride ion. So X is a chloride ion. So now we've identified X, we need to identify what is in Z, what anion is in Z. So here we can see that there is no change when the acid is added, that there is a yellow precipitate formed when the silver nitrate is added. So we need to know this is an iodide ion. And just to recap for you, when we add this dilute nitric acid and then we add our silver nitrate, we get 3 sets of results for the halide ions. If we get a white precipitate, and we know that shows the presence of chloride ions, we have a cream precipitate, we know that that shows the presence of bromide ions, and if we get a yellow precipitate, then it shows the presence of iodide ions. And these are the facts that I have used here. So if you're not familiar with these, make sure you go away and get learning them, because we need to know these tests. The student thinks that solution Y contains carbonate ions. To confirm the presence of carbonate ions, 1 more test is required. Describe this test. So if you think of what we've previously done, we've added some acid and we saw that it bubbled. Now that is always the first part of a test for carbonate ions. But that isn't enough. We need to test for what that gas formed is. And if that gas formed is carbon dioxide, then we've confirmed the presence of carbonate. So what we need to do to test for this is to bubble the gas through lime water, and then we need to know what we will observe if carbon dioxide is present, which of course indicates the presence of carbonate ions originally. So if CO2 or the carbonate ions present, then it will turn cloudy. You can also say milky or white. All of those are a correct observation in this question. So now we're told that substance A was added to the solutions to identify the cations in X, Y, and Z. We are told when it's added to X, we get a brown precipitate, Y, we get a blue precipitate, and Z, a green precipitate. So we need the identity of substance A. So the answer to this is going to be sodium hydroxide. And that is the substance that we add to solutions of certain cations to test for their presence. The student identifies the cation in solution Z to be Fe2+ ions. After A is added to solution Z, the green precipitate gradually turns brown. Suggest why the green precipitate originally formed turns brown. This is quite a challenging question where we need to use our broader knowledge. So here we need to state that the green precipitate that was formed was actually iron 2 hydroxide. And when we leave it in the air, what's going to happen is this iron 2 hydroxide will react with the oxygen in the air and it will become oxidized. And so it will become oxidized in the air, which makes it turn brown, as it will become an Fe3+ ion instead. The student determined that solution Y contained copper 2 carbonate, CuCO3. And here we're asked to write down the chemical formulas of X and Z. So to do this, I'm going to write a little table here, just to organise all the information that we know about X and Z. Now I'm going to look at the table that they gave us in the earlier part of the question. So we know we got a brown precipitate when sodium hydroxide was added to X. And we need to know that that means that Fe3+ ions were present. Next up in Z, we know we got a green precipitate when sodium hydroxide was added. But that means that Fe2+ ions were present. We need to have that knowledge in our memory. So now we can write those down. So we know that X contained Fe3+, but also Cl- from earlier in the question. And Z has Fe2+ and I-, again from earlier in the question. So to get the formula for X, we need to look at those charges. We need to balance that 3+ charge with 3 minuses. So for that reason, we need FeCl3. Over with the Z, we can do something similar. Fe2+, but I just minus, we need a 2- to balance the 2+. So for that reason, we need 2 of the I-, so the formula is FeI2. So writing up our answers finally on our answer line, we have FeCl3 and FeI2.
Cracking is an important process carried out on longer chain hydrocarbons after fractional distillation. Here we're asked to explain the importance of cracking longer chain hydrocarbons. And this is a 3-mark question, so we need 3 good points. So our first point, we need to state that there is a much higher demand for the shorter chain alkanes than there is for the longer chain alkanes. Now this is important because it means that we're going to make more of the longer chain alkanes than we really need. So cracking can make use of those by cracking them into shorter chain alkanes. So now for our next point, let's have a think about what we make during cracking. So one of the products of cracking is a shorter chain alkane. And the reason why this is so useful is because we can use that for fuels, for example, making petrol. The other product in cracking gives us our third point here. We make an alkene as well during cracking. And alkenes are particularly useful because we can use them to make polymers. So here we have our 3 points explaining the importance of cracking longer chain hydrocarbons. 1, there's a higher demand for shorter chain alkanes. Then those alkanes can be used for fuels, and the alkenes can be used to make polymers. So now let's look at this calculation question. Dodecane can be cracked to form an alkane and propene, as shown in this equation. We're asked to calculate the maximum mass of propene that can be made by cracking 1 kilogram of dodecane. The molecular mass, MR, of dodecane is 170. So the first thing I would do here is I would write the equation nice and big at the top of my page. So here you can see we have C12H26 makes C9H20 plus that propene of C3H6. And there's only 2 bits this question wants, that's the dodecane and the propene. So now I'm going to write a column with 3 rows of information, the mass, the MR and the moles. And I'm going to write in all the information I know. So I know that I have 100 grams or 1 kilogram of the dodecane. I know I'm told the molecular mass of dodecane is 170, and we can also work out the molecular mass of the propene that we're being asked about. So the formula is C3H6, so the MR would just be 3 times 12 for the carbon plus 6 times 1 for the hydrogen, and that gives us an MR of 42. See, so now our table's looking pretty fleshed out. We have enough information to work out the moles of dodecane. Moles we know is mass divided by the MR. So in this case, the moles of dodecane will be 1000 divided by 170. And that gives us 5.88 moles. So I would fill that into the table here. Now we're being asked about propene, and moles is great because it links the two. Here you can see in this balanced equation you just have one of each, the dodecane and the propene, which means we have a 1-to-1 ratio between them, which means we must have the same number of moles of propene as we did dodecane, 5.88. So now we know the moles and the MR of the propene, we can easily calculate its mass. So mass equals Mr. Moles, MR times the number of moles, so we can substitute in the values that we already know to get our answer. So the mass of propene will be 42 times by 5.88, and that ends up giving us an answer of 246.96 grams. And of course that's one version of the answer. We can write that there in our answer line. However, you could also give the answer here in kilograms too. So whereas 246.96 grams is the answer in grams, you could also give your answer as 0.247 kilograms. Both are correct and will get you your marks.
Well done for making it to the end of the paper, lovelies. I'm really, really proud of all of your hard work.